So this is a review so far. We know that the original design of IP was that the address would be 32 bits long. Talk about the INE in just a moment. Now, the way computers see it is it's just a single string of 32 bits. You know, it's 32 bits end to end of an address. So really, you know, your computer says, oh, my IP address is 32,147,205. That's my IP address when I add up those 32 bits. If I was to convert that 32-bit number into a decimal number, it'd be some monstrously large number in the billions. But we as human beings can't really work with that. You know, if I ask you what the IP address is of your laptop, hopefully you're not going to say, oh, it's 7,605,202. I'm going to walk away and I'm going to forget that 15 seconds later. So as human beings, we said, okay, that 32-bit number, we have to come up with a way that we can use it, that's readable to us. So basically what we did is we said, okay, let's take that string of 32 bits and cut it into 4 equal pieces, 4 bytes, right? Each byte is 8 bits long, so 8, 8, 8, and 8. That gives us 32 bits. And then of each octet, of each byte, we will convert that byte into a decimal number, and then we'll put dots in between them. So now we'll have 4 decimal numbers instead of just one monstrously long decimal number. So instead of seeing this, you know, if I gave you that as my IP address, well, that's fine for my computer, but as a human being, after I give you about the 9th bit, you're going to forget everything else. So we cut that into 4 equal pieces, convert it into decimal, and we get what's called dotted decimal. And that's actually the real dotted decimal equivalent of that 32-bit number that you see right there. The first 8 bits translate to the number 2. The next 8 bits translate to the number 234. The third series of 8 bits translates to 107. And then the last octet, the last byte, is the number 18. And so that's how we as human beings manipulate and read and type in IP addresses. And this is what we call dotted decimal notation. Computing devices don't need this. They're perfectly fine with a string of thousands of bits. This is just for human convenience. Okay, so we talked about how on a broadcast domain, data could go out in one of 3 different ways: broadcast, unicast, and multicast. And I said that when I'm transmitting data, when my NIC card, when my laptop is transmitting data, it needs to structure the layer 2 and the layer 3 address to be appropriate to what it wants to do. So how does it do that? Well, we talked about multicast. Multicast is actually real easy to represent. In the world of layer 3 at IP, if you take a look at the destination 32-bit address, so it's 32 bits going out as a destination address, if the first 4 of those bits match 1110, that is a multicast address. We don't care about what the remaining 28 bits look like. As long as the first 4 bits take that pattern, that means this is a multicast, one to many. Broadcast. Now in the world of IP, we know that an IP address, it's subdividable. Part of it represents the network, the broadcast domain. The remaining part of it is what we call the host bits. Now in the case of a broadcast, we've got 2 options. Now in both of them, look at this. One thing they both have in common is the host bits are all 1s. So in an IP address, if we take our focus away from the network portion for a moment, we forget about that and we move to the second half of the address, the host portion of that address. If you ever see a 32-bit number that's an IP address in binary, and you see that the host bits are all 1s, just a continuous string of 1s, that means you're looking at a broadcast address. Now there are 2 different flavors of broadcast address. This first one right here that says any.111111111. Let's say that on the broadcast domain I'm on right now, my laptop is connected to a broadcast domain. Let's say it's been decided that the first 8 bits to identify my network is going to be in decimal the number 5. So I am on network number 5. 0000101. I'm on network number 5. If my laptop wants to send out a broadcast to just the devices in my own broadcast domain, so this is what's called a directed broadcast, sometimes called a subnet broadcast. I want to talk to everybody in my domain only. Then the way I would structure my destination IP address is I would say in the network portion 5, because that's my network, I'm on network number 5, and then in the host portion is where I would put all of my ones. Or if I'm in network 199, the network portion would say 199 in binary, and then the host portion would be all ones. And that's a way of saying this is a directed broadcast. It's directed to everybody within my domain, and my domain only. The second one down, where the entire 32 bits end to end is just a continuous string of ones, that's what's called a general broadcast. That means it's to pretty much the entire world. Of course, it's not going to go out to the entire world, but that's what a general broadcast is, where the entire 32-bit number is all ones. Vast majority of time, I'd say probably, 90% of the time, when a laptop or a host, any host, needs to create a broadcast, it will choose the second option there. It'll create a broadcast where the destination IP address is just 32 bits of all ones. And if we convert that into dotted decimal, that would be 255, 255, 255, 255. So pretty much any protocol you can think of that utilizes broadcasts like ARP, DHCP, at layer 3, the layer 3 destination address will be all ones, the general broadcast address. Off the top of my head, I can't think of any protocols that create directed broadcasts, which is the INE.1111. There probably are some, I just can't think of any right now that actually do that. And then unicast. So we know that unicast is one-to-one communications from one device to another device. And so it's pretty much any pattern that does not match the previous two patterns, except with all zeros. We know that any IP address that starts out with the first octet being all zeros, that is reserved. That's called that's actually used more for routing. That means it's going to everyone. It's not really going to everyone. It's what we call the default route, basically. But it's not really reserved. It's a reserved address. So what's the takeaway from this? If you see a 32-bit pattern in binary, and you are told that that is an IP address, now if somebody asks you on like a multiple choice question, identify, is this IP address in binary unicast, multicast, broadcast, or none of the above, you should be able to do that, because now you know what the pattern looks like in binary to identify those three. Okay, so up until this point in time, we've still retained this idea that an IP address was 32 bits long and only the first 8 bits represent the network. We had 24 bits of host space, 8 bits of network space. And I mentioned at the very beginning that really only left us with 254 networks, which back in 1969 was tons. But as we started getting into even just a decade later, into the late 1970s, it very quickly became apparent that, this isn't going to work. 254 networks is not enough. There's networks popping up all over the world, which are modems, satellites, and using Ethernet. We need more than 254 combinations. So the designers of IP said, okay, let's take this 32-bit number now and look at it a little bit differently. How can we look at that 32-bit number and somehow come up with more than 254 networks? Well, let's do this. Instead of just looking at the first 8 bits for the network, why don't we look at more than that? Why don't we take those host bits, sacrifice some of the host bits, and add them to the networking section? And they came up with classful addresses. So in 1981, and some of you watching may not have even been born back then. So in 1981, classes of addresses were introduced. So Class A, that was like the original way of doing it. A Class A address meant that the first 8 bits represent the network. The remaining 24 bits were for the host. So that was a class A, just like the beginning when it first was invented in the late 1960s. But then they said, okay, well, we'll also have a class B address. In a class B address, instead of the first 8 bits representing the network, the first half of the address, the first 16 bits, represent the network. In a class C address, now 75% of the bits represent the network. The first 24 bits represent the network, and only the last 8 bits represent hosts. Now the question is, okay, well, if I put a 32-bit number in binary on a laptop or a PC, how does it know how to interpret that 32-bit number? Let me bring up a whiteboard here for a second so we can draw this. Okay, so here I've got some device. I'll just go ahead and draw a laptop or a PC, whatever. And I'm going to give it some 32-bit number. Actually, I'll start off by giving it a 28-bit number. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 6, 7, 8. There's a 28-bit number. And I'll leave off the first 4 bits on the front. Okay, so in the world of classful addressing, when you put an IP address on a device, 32-bit number, the first thing that device did was look at the very first bit. If that first bit was a 0, then that device says, okay, now I know exactly how many of these bits represent the network. If the first bit is a 0, that is a class A address. And in a class A address, just like the old days, the first 8 bits, the first byte only, is used to represent the network. And then all these other bits here is a unique host identifier for this one unique machine on this network. Now let's say he looks at his 32-bit address and it starts out with a 1. Then he says, okay, well this is not class A. I need to look a little bit further to figure out what the class is. If he sees that after that the next bit is a 0, he says, I'm done. This is a class B address, which means 4, 5, 6, 7, 8, which means that the first 16 bits represent the network. So you can see here that with a class A address, it's just like the old days. I've only got 254 unique numbers I can come up with. All zeros is reserved, all ones is reserved, and then I have 254 combinations in the middle of that. So 254 networks. But if I tell my device, oh, your address is a class B address, well now I've got 16 bits of network. That gives me tens of thousands. Actually, I think 16 bits gives you about 65,000 combinations of unique numbers you can come up with, a little bit more than that. So now we can see, oh, I've got a lot more networks available with 16 bits, but what's the downside? You know, with a class A network, yeah, I've only got 254 of them, but on each one of those networks, I've got a lot of hosts, right? I've got 24 bits of host bits on a class A network. That's 2 to the power of 24. I think that's something like 16 million or something like that. So that means on one single cable, you could have about 16 million devices all in the same group, all with the same network address. Not really feasible. With class B, I've got a lot more networks available to me, but I'm sacrificing my host space. Now instead of 24 bits for host, I've only got 16 bits for host, which is still an awful lot. That means with class B, I've got well over 65,000 networks to me, and each one of those networks also has 65,000 combinations of hosts it can have on that one wire. But they didn't stop there. They said, okay, if I give a device a 32-bit number as an IP address and it sees that the first 2 bits are 11, then it looks at the third bit as 110. Now it says, okay, now I know that of my 32-bit number, the first 24 bits, which would extend right about here, is my network address. And that's our Class C address. So with a Class C, you can see there's even more networks. We've got 2 to the power of 24. So we've got millions and millions and millions of Class C networks available. But each one of those Class C networks only has 8 bits left over for host space. And we know that the all zeros and the all ones hosts are reserved. So that means we've got 254 hosts for each Class C network. So those are all the networks that were designed for unicast transmission, for one-to-one transmission. And so you can see here, if I've got a Class A network that starts out with 0, so if I've got 0, 1, 2, 3, 4, 5, 6, 7, dot anything, well, we know that this number is reserved. Can't start out any network with all zeros. And we also know that this number is reserved. Can't start out any network with that. So that basically tells us that from 1 dot anything through, actually, wait, hold on a second. It's still got to retain the 0 in the first bit. So we've got in the middle here 1 dot anything. That's our first usable Class A network through, and that number right there was 127. And that gets us back to our slide. That's where we saw this. Class A networks, technically you can't use the all zeros, so 1 dot anything through 127 dot anything. Now also, this gets a little sticky here, but technically 127 is also a reserved number. Just like a network number can't start out with all zeros and it can't start out with all ones, 127 is also a reserved number for special usage. It's called the loopback network. If you ever want to Google that, the loopback network is anything that starts out with 127. So really, in your pursuit of your CCNA, what you need to memorize a couple things. You can identify a Class A network by the binary. If the very first bit is a 0, that's Class A. And you should probably also memorize the dotted decimal. So I'm just going to put a line through this because 127 is reserved for loopback. So 126 dot anything. So the usable range of Class A networks are 1 dot anything up to 126 dot anything. That's the usable range of Class A networks. Now when we go into Class B networks, this starts out with 10. Well, 10000 is the number 128. And if I keep that pattern of 10, get rid of some of this here. 1, 0, and then 1, 2, 3, 4, 5, 6. And then 1, 0, 1, 2, 3, 4, 5, 6. So that's my full range of Class B, because we know Class B has to start with 1, 0 in binary. So if I translate that back into dotted decimal, that's 128 dot anything up to 191 dot anything. So that's also something you should memorize as you pursue your CCNA certification. Is that Class B is recognizable in binary by any IP address that starts out with 10, and it's recognizable in dotted decimal by any IP address that falls within the range of 128 up to 191. And then finally, we have our Class C addresses. We know that class C in binary starts with 110. So the smallest number we could come up with that retains that pattern is that. And the largest number we could come up with that retains that pattern is that. So here we have 192 dot anything. That's the smallest class C network, anything that begins with 192. And 223 dot anything. So this is your full range of class C networks. Anything that starts out with 110 in binary or in dotted decimal, anything that falls within the range of 192 to 223. And that's what we see here. Class D networks, this is reserved for multicast. So if I've got that situation where I'm sending one sender, one transmitter is sending a single stream of data that multiple devices are going to pick up. If I don't want it to be for everyone, it's not a broadcast, it's a multicast, then you would use an address in the class D space. And the way you would recognize that in binary and you see the pattern right here, are the first 4 bits. So the smallest multicast address is anything beginning with 224 and that's the largest multicast address, which is 239 dot anything. So that's your range of multicast addresses, all starting with 1110 in binary, in dotted decimal falling within the range of 224 to 239. And then the last range of networks is, I wouldn't even say networks, the last range of classful IP addresses is what's called the class E. This was originally known as the experimental range. And if we go to our binary once again, you can see it's going to be the next pattern available to us. So class E experimental addresses start out with 1, 1, 1, 0. So the first 5 bits are 1110. You're never going to see any IP packet with a class E source or destination. It was reserved as future use and it never really came to fruition. So even today, here we are in 2015 where IPv4 networks are almost entirely gone, almost entirely used up. This space has never been utilized and will never be utilized, class E. If you're curious as to why, if you're watching this in the live class right now, in the files section in the upper right, you'll see I've included a PDF of these slides, and in the notes section, I've included a URL in there that talks about why class E is never going to be used. Just to really briefly summarize, for the last, 3 or 4 decades, the IP protocol stack, the code that implements IP, has been written in such a way that whether that code is implemented on a router or a laptop or a tablet or a smartphone, every device has always recognized that class E is not usable. If you try putting a class E address on your laptop or on a smartphone or on a router, you'll get an error message because it recognizes in the code that this is reserved for future use. So some people have said, well, here we are today in the modern world. We need this space. We've run out of IPv4 addresses. Let's reclaim the class E so we can get some more space out of it. Well, that URL in the PDF goes into a little bit of detail. Basically, it says, well, let's think about that for a second. With the way that people are using IP these days, with how many new networks are coming online every single day, if theoretically we could use the class E space, that might extend the usable life of IPv4 for maybe another 5 or 6 years, maybe. But what would that require? that would require that all the software developers that developed Windows and Linux and the Apple operating system, they'd have to go back into their code, rewrite the code so that this was now an acceptable address. It wouldn't spit out an error. It would recognize that as being useful. And what about you that already own a laptop? How are you going to go into your IPv4 code and change it so that it now recognizes that this is okay? It's all right to see that. You can't. So they said, look, the time and the effort it would take to take all the new equipment that's being developed to recognize that as being all right, and to somehow go to everybody's existing smartphone and tablet and PC and say, okay, it's okay now, it's all right. It's not theoretically possible to do that. It's just not feasible to do that as an end result to only give yourself maybe 5 extra years of life of IPv4. So that's why Class E will never come to anything. Just won't be usable for anything. Now somebody has asked, so Ganesh has asked me to elaborate a little bit on what this concept is of the loopback address, which is basically anything beginning with 127. Basically the way I understand this is that any device that's running IP, whether it be a router or a laptop or a tablet, when you tell that device, hey, I want you to create a packet, and I want the destination of that packet to be 127 dot anything. The way that device interprets it, it says, okay, well that means that basically I'm testing myself. I'm testing to see if my own IP protocol is working and is functional. So when you tell a device like a laptop or a PC or a router to create a packet going to 127 dot anything, it will create that packet, but it never leaves the brain of the device. It will never actually go on the wire and go anywhere. It's like you're talking to yourself. It's like, hey, IP, are you there? Yep, I'm here. Okay, we're good. And so that's what they mean by loopback. It doesn't leave the device. It's basically a way of just testing to see if your own IP protocol is working. So for example, if I open up a DOS prompt here, if I ever was wondering, I say, oh, you know, I can't get to the internet, I can't get to my email server, I can't get to anything. I wonder if there's some bug in my Microsoft implementation of IPv4 in my laptop. Could IPv4 be buggy in my laptop? Well, I can test that by just saying ping 127 dot pretty much anything, 567. And the fact that I'm getting a reply tells me that my own local implementation of IPv4 is okay. I've just basically pinged my own CPU. So that's what the loopback network is used for. And it really doesn't matter what it is, 127.88, 99, 100, just the fact that it's beginning with 127 tells the IP protocol implementation that this is a loopback test. And you can do this on a router or a laptop or anything that gives you the ability to send a packet to 127. So that's what that's reserved for. Okay, well, if you don't have any questions for me, I've got some questions for you. So I had promised you that during this presentation I'd have some periodic quiz questions that would pop up. So I'm going to give you a couple of them right now, and then we will take our first break. So here's what I'm going to do. These questions should be pretty quick for you to answer, so I will display the question. I'll maximize it here so you don't see me. And when you see the question, I will give you 30 seconds to think about it, to come up with the answer. You don't have to type in the answer if you don't want to. Just try to come up with it on your own. And then after 30 seconds, I will show you the answer, and we'll talk about it. So let's go to question number 1. Identify which of the IP addresses below belong to a Class B network. You have 30 seconds. And if you're watching this as a recorded session, you can just press the pause button right now to pause this recording, and then play it when you think you have the answer. Okay, so it's been 30 seconds. So which of these are Class B networks? Here is your answer. Answers C and D. We know that in binary, any IP address that begins with a combination of 1, 0 is a Class B network. That's why answer C is correct. And we know that if it begins with 1, 0, that means the range of Class B networks is anything from 128 up to 191. And that's why Answer D is also the correct answer. Let's go on to the next one. Identify which of the IP addresses below belong to a Class C network. Okay, time is up. So Class C network, the answers would be answers B and E. With Class C, anything in binary that begins with 110 is Class C. And in dotted decimal, that means your first octet is going to fall within the range of 192 up to 223.